So before we talk about the homework problem, I want to remind you that there is a class participation assignment that I'm asking you to do, which is completing the bisection method and false point method that is fully automated as an Excel file. I already gave the starting point. You need to finish up your own file and upload it to Canvas. We will open this file and look at it in a binary sense, whether there is reasonable effort put in the class for you to try the problem or not. If you just didn't upload or uploaded a blank file or nothing that is beyond what we provided, we won't give you credit. If it's reasonable effort, we'll give you credit. It's not about the answer, it's about effort. And this time I had it open until like September 14th, September 12th, September 14th until class starts. In the current module, that is module 2, you are going to do some kind of programming in class and you will upload it during class time. So you will have to actually come to class in order to be able to do this. Which lecture we might do this, I'm not sure. Maybe the third or fourth lecture in this topic. But you'll have to do this in class and upload it within class time. Since it's the first time, I'm giving you time until September 14th to get this in. Okay, that makes sense? So coming back to the homework. So this is problem 8.48. That is the assigned homework problem. You are asked to solve this problem using all the numerical methods we studied in this first module. So it has come to my attention that many of you are having difficulty in setting up the equation that needs to be solved. So I'm just going to give you some hints to get started to set up the equation that you need to solve. And beyond that, you will have to do the work of actually solving it. Okay. So the problem involves fluid mechanics. So we can't talk about this problem without talking something about fluid mechanics. What we are doing here, I'm going to stop my screen share here for a second so that the recording will have these written down. All right. So what you have is an object like a sphere that is falling due to gravity and it is falling through air. So obviously gravity acts downwards and the resistance to the motion or the drag force is acting upwards, countering gravity. When these two are in balance, or if you go back to your dynamics, you can write an equation of motion, mdv dt equal to, let's say, gravity minus drag force. This is the basic equation of motion to this particle or sphere, whatever you want to call it. Until the drag force catches up with gravity. And why would drag force vary with time or vary with velocity? Because drag is always related to how fast you are moving. If you're not moving at all, it's non-existent. So this will initially be 0 and it will slowly start increasing as the velocity picks up. But gravity is a constant force. From the moment or from the beginning to end, it's the same value. So it's like this. You have gravity to be a constant force, whereas drag force scales something like this. So once they equal each other, this acceleration goes away at terminal velocity. That is, when gravity equals to the drag force at that terminal velocity, then the two forces are in balance, which is what this equation is. The left side is, I've written it as weight or gravity force, density multiplied by volume times acceleration due to gravity. And the right side is drag coefficient, which is CD, multiplied by half rho v squared, multiplied by pi d squared, which is the frontal area. Frontal area facing the flow. Now this is all some background that you may or may not know, but when you're solving these kind of problems, it's not about knowing everything, it's about distilling information from what is given. You're with me so far? That we have an equation that relates gravity force to drag force, and drag force depends on the object's velocity. Now, in the problem, they have told you that when Reynolds number is less than 0.1, the flow around this sphere is laminar, and they have given you an expression for CD, or they have given you an expression for the terminal velocity directly. That is, in the problem, for Reynolds number less than 0.1, the expression for terminal velocity V is given directly. And let me write that down here. That expression is V equals G over 18, density of the solid minus density of the fluid divided by viscosity of the fluid times diameter squared. For Reynolds number more than 0.1, or in other words, for turbulent flow, CD is given as 24 over RE plus 3 over square root of RE plus 0.34, where Reynolds number is density multiplied by velocity times diameter divided by viscosity. You know what is Reynolds number. And they have also given you the expression for velocity as V equals square root of 4 times G multiplied by the difference in density times diameter divided by 3 times CD times density. The problem statement, that is the textbook or the authors, actually I feel confused you by including one sentence here or including one extra word here. In part A, they say combine equations P 8.53 or 8.48.2, P 8.48.3, and P 8.48.4, and then the problem goes on to express f of v equal to 0. They should not have included this. They should not have. This is opinion I'm now offering you. They should not have included this. That is why most of you are all confused. If this is your equation, just look at this. This equation involves CD, which depends on Reynolds number, and you know Reynolds number depends on velocity. So if you just look at this equation, here the left side, which is velocity, and here is right side is a quantity which also depends on velocity. And to solve this equation, using any method of your choice, use an initial guess using this equation. I'll put it as equation star, using equation star. This is all you need to do. Here is your problem, or here is the equation to be solved. I'll write this as f of v equal to 0 with an initial guess that is coming from here. Once you solve, that is after solving for V, compute the Reynolds number and check if it is greater than 0.1, which would imply that this is a turbulent flow or not laminar flow. Yes.
So like for the bracketing methods, we need a range. Are we using that initial, like how do we come up with a range?
Come up with a range. You are trying to solve this f of v equal to 0, right? You would graph this function and see where it intersects 0, and you can choose any range that contains that point of intersection.
So okay, so we do that, and then if we're looking for initial guess, we get that from the v value.
Yeah, use this as the initial guess because it sort of is like an imperfect solution to the problem, but it will still lead you to the correct answer. Yeah. The textbook writers introduce confusion by including this in the problem statement. If they had not done that, we would not be confused. Yes.
You want to see all the iterations done by hand?
Yes. Yes, I want the iterations done by hand because it's the only problem we are evaluating you. And also we want you to write a summary statement in the end, comparing the different methods with regards to their accuracy, the number of iterations. That I think that is mentioned in the problem statement. The problem statement that I put on campus, not the one in the book. Yes.
So okay, the other question. So in your problem statement, you had a table comparing the values. We're comparing the v values, not the Reynolds number values.
V, yeah, V. Okay. The quantity which you are solving for.
Okay.
That is, you might solve for V, you might solve for Reynolds number. You could multiply the left side by a constant like density, diameter divided by viscosity, turn this into Reynolds number and solve the whole thing for Reynolds number. But at the end of it, you need to have, if you have Reynolds number, you have velocity and vice versa. Okay, so these usually physics or engineering problems, there's no one way to solve it. I can't put out like, get me V. I'll say get me a solution and you have to define what that solution will entail. Okay. So please take a look. Ask me any questions. If not, we can move on to the next unit. In conclusion, you have to solve this equation for velocity or Reynolds number with an initial guess using this equation star. And after you obtain the value for velocity or Reynolds number, you will have to ensure that the flow is not laminar by checking if the Reynolds number is more than 0.1. If you were in the exam and this problem came to you and this clarification wasn't provided, what would I have done? I would look at this equation, first realize that in this equation, there is nothing to be solved iteratively. This is a linear equation. Velocity equals a bunch of constants. There's nothing to be solved here. Okay? If I look at this equation, yes, there is definitely nonlinearity going on. So this will need to be iteratively solved, and I might pick my own initial guess or use this for an initial guess, but I would definitely solve this and not worry about solving this because there is nothing to solve. Okay, so if you have exam problems, at least in my course, please do not stand up and give me a speech about how that problem is wrong. Whatever is on the sheet is fair game. Exercise your judgment, document your decisions, and send it to me for evaluation. Do not make a scene there standing up and saying, oh, this is wrong, you must have thought of this or that. No, I don't want your lecture in the exam hall. Tell me that later or before, not in the hall. Yes,
So going back to the graphical method, we had the chart with the iterations and the error. How does the graphical method, like the increments, how does that translate into how many iterations? Like, how do we,
that is, if you did your graphing, suppose you are thinking about f of v equal to 0. And suppose f of v had this type of a behavior, and here is the root. Okay. Now, if you put it in your calculators, graphing method already has some kind of numerical method programmed inside in your calculator. You will actually get the final answer. But in the old world, if you still had graphing paper and it had increments of say 1 millimeter or whatever, you could choose to plot it say 0, 1, 2, and so on. So there is a certain finite resolution with which you can narrow down the root. You can't get it with 5 decimal point accuracy. You will get it say between 0.1 and 0.9 or whatever. And you'll have to work out the remaining decimal points by using any iterative method of your choice. Okay, so graphing method will keep giving you sort of like in bisection method, you will generally do check f of 1 and then check f of 2 and see if this is negative and this is positive. You will think it's between 1 and 2, right? Graphing method is sort of the same. Yeah. So I think I've made myself very clear that anything that's on the exam sheet is fair game. Even my mistakes, I'll try not to make, but even if I make a mistake, you as an engineer call it out in your exam sheet and then we'll honor it. Okay, that's how engineers take decisions. All right, good. So then moving on, today from 1 to 2 p.m. I plan to hold a recitation session, which is optional. All of you are welcome to attend. We'll record it and post it in Canvas. Okay. All right. So then, are we good? Can we move on? So we saw in module 1 how to solve nonlinear equations iteratively. Nonlinear equations do occur in engineering practice, but linear equations are much more common. Like for example, if you have systems of equations which are linear and algebraic, meaning you have say a1 x1 plus or a1x plus b1y equal to c1, a2x plus b2y equal to c2. This is two equations in two unknowns, x and y. You could similarly write more equations. You can write a1x plus b1y plus c1z equal to d1. You can write three equations in three unknowns and so on. You can keep on doing this. Before we learn methods to solve these, I would like all of you to pitch in some examples of engineering situations where you would end up with a set of linear equations to solve, which will be a step in your solution process. I think the word you're looking for is trusses. Yeah. So analysis of truss network. So can you also elaborate a little more, telling me how you end up with these equations?
Let's say you have like a single point that has like multiple different like forces acting on it. You have like an X and a Y coordinate system, and you have to find each force by separating into its X and Y. And if you have two forces acting on it, you can find both of them by setting up the equations.
Nice. So what you're saying, if I paraphrase that, you would apply a force balance on this joint. And this joint is subject to forces from each member. And each member's force can be resolved into a global x direction and a y direction. So that you would apply a force balance along x, where all the forces acting along this direction would be summed up. And same for the y direction. So you would end up with an equation that describes the displacement of this link of this joint in both x and y directions. So if you do this for multiple joints, you are going to get an equation for each of those joints, which together will make up a system of linear equations. I'm sure you have seen some of this in your statics class. Any other example? The reason I ask is I don't want you to think all this is pointless. I would like you to think that this connects back to what you have done in other courses. We saw one structural example. Anything else? Anything mechanical? Spring block damper systems? Or yeah, yeah.
In any system of equations with forces and velocities, like different objects would be in tandem.
Like connected objects, like system dynamics or robotics, where you have each object connected to several other objects and their equations of motion are all coupled. So each variable could represent the displacement or velocity of a given object, and the displacement of this depends on the displacement of this and so on. So they are all interconnected. Okay. So we'll start with an example. Okay. Let's just do one example and then try to generalize it as a technique. We're trying to do example 9.5 from the textbook. Use Gauss elimination to solve this three equations in three unknowns. The name isn't important. We'll see the different names later, but the method is sort of intuitive for us to try. 3x1 minus 0.1x2 minus 0.2x3 equal to 7.85. 0.1x1 plus 7x2 minus 0.3x3 equal to minus 19.3. 0.3x1 minus 0.2x2 plus 10x3 equal to 71.4. Let's do a check of what we already know. There is, before this class, if this is presented to you, apart from saying I will punch it in my calculator, what would you do? Sorry, I had matrices.
Yeah.
So you would write this as a matrix A times x equals B, and then you would write x equals A inverse of B. Okay, what other techniques are you aware of? This requires getting the inverse of A, which is actually a lengthy process. Sorry, can you elaborate? That is, you eliminate them step by step, right? Okay, any other ways to solve this equation?
Isn't there a way where like you can make the numbers on one of them line up and like you can subtract and cancel out?
Yes, that is, you would want to make the coefficients equal. Say, for example, you would multiply the second equation by 3 and then subtract 2 from 3. So that x1 is gone and you're left with only 2 equations and 2 unknowns. And then you would do the same until you're left with only 1 and you would solve for that one. So what you said as substitution and what you said as basically matching the coefficients, we are going to do both of that in a sense, and that method is what is referred to as Gauss elimination. Basically, Gauss came up with a way to do this systematically and algorithm and make it into an algorithm. Okay. So how do you do this? whatever you said, we are going to do this, but without paying attention to the coefficients, we'll just take the equations one by one and try to do it without paying attention to what coefficient, so that it can be turned into an algorithm, okay, not just for this problem, but for any problem. So if I take this term here, I'll call this A11, okay? So I have a system of equations where I name this as A11x1 plus A12x2 plus A13x3 equal to V1. A21x1 22x2 plus 23x3 equal to V2. And then A31x1 plus A32x2 plus A33x3 equals B3. You can see the numbering convention. A11 means first row, first column. This again ties back into writing this as a matrix, where you can also equivalently represent this as AX equal to B, where A11, A12 are all elements of the matrix A, and X1, X2, X3 are the elements of matrix B, matrix X, and B1, B2, B3 are the elements of matrix B. All right, assuming A11 is not equal to 0, what would I want to do? I want to divide the first equation by A11 and second equation by A21 and subtract 1 from 2. So if I divide the first equation by A11, I'm going to get x1 plus A12 divided by A11 times x2 plus A13 divided by A11 times x3 equal to B1 divided by A11. So this is first equation divided by A1. Second equation divided by A21. So I have x1 plus A22 divided by A21. I'll move out of your way, sorry. Yeah.
Subtract 1 from 2.
I'll say this is modified 1 and modified. I want to subtract modified 1 from modified. Yeah,
Are we not taking our original sign into,
we'll just call them as A12, and then you can say A12 equals minus 0.1. So we want to subtract modified 1 from modified 2, which would be something like A22 divided by A21 minus A12 divided by A11 x2 plus equal to B1 divided by A11, sorry, B2 divided by A21, B1 divided by B1.
So you divide the merger stuff, they're divided first, equation by A11, are you dividing the side as well?
Yeah, yeah. Entire equation, both left and right sides. So ugly as it may seem, if you have your original equation and you have this, all you need to have is, if you're doing this on MATLAB, try to have these labeled. That is, you create the variables A11, A12, etc. at the start, assign them these values, and then you have to punch in these formulas for you to get moving further. Okay, this method here is one of the least preferred because it's just involving a lot of operations. It's highly prone, or it offers so much chance for making mistakes. You will have to divide so many times and multiply so many times, subtract. Just not something that we want to use. Okay. So even though I'm introducing this Gauss elimination method to you, I'm also telling you that if you have to choose a method, this would be your last choice. Because there's not a very efficient method. You can see how many operations that you have to do. So if you're implementing it, it's not very efficient. Okay. So what I'm going to focus on is not actually trying to make you do something that I don't feel is useful. I would rather have you do this method called Gauss-Seidel iteration, which is much more intuitive, which will get you answers in an intuitive manner rather than doing this laborious calculation. So as far as this unit goes, I want you to be aware of this term Gauss elimination, but I'm not going to question you or test you on that. I'm going to focus more on a method we are going to see called Gauss-Seidel iteration. Okay, so you can take this to completion. That is, you can work out what type of equations you will get in order to eliminate x1 first, and then x2, and then finally get x3, and then substitute back to get x2 and x1. It will just take up our entire time. I don't want to do that. Okay, so let's move on. So in the first unit, I remember that I assigned fixed point iteration as a self-study for you. In the same spirit, we are going to have you look at Gauss elimination by yourself, and we are going to focus more on I'm just trying to find the correct section number. Section 11.2, that's what we are going to focus on. Gauss-Seidel iteration method. We are going to see this on pencil and paper, as well as we are going to build a MATLAB code. You are going to build a MATLAB code as we discuss this in class. Okay. So for today, we'll do this like pencil and paper, but I strongly recommend all of you to bring your laptops next lecture, where we will attempt MATLAB programming. Okay, so you've been given advance notice. So if you're still writing down, I'll wait for half a minute for moving on. Self-study. So if you are done writing, just relax, sit back. We'll just see how this Gauss seidel method should be implemented or how it works, okay? So if you have 3 equations in 3 unknowns or 5 equations in 5 unknown, any number of, any size of equation system, that's fine. Look at your first equation, okay? What we want to do here is to step 1, rearrange equation 1 for solving for x3, let's say. How would you do that? X3 equal to b1 minus a11 x1 plus a12 x2 divided by a13. Please, no need to write down. I promise I'll give you time to write. Okay, put your pencils down. This equation is being rearranged to solve for x3, but what is the catch? You need x1 and x2 in order to actually solve, right? You can do the same with the other 2 equations. You can take the second equation and rearrange it for x2, say for example b2 minus a21 x1 plus a23 x3 divided by a22. Yeah. Actually, just for symmetry's sake, I'm going to rearrange equation 1 for solving x1. You'll see why that is a convenience, because that will give us. This is why I said don't write. A12 x2 plus a13 x3 divided by a11 and x3 equals b3 minus a31 x1 plus a32 x2 divided by a33. You can use the 3 expressions to get x1, x2, x3, but each one also has these unknowns, and that's why this becomes a iterative technique where you make an initial guess. Let's start with some kind of an initial guess. So we'll write iteration number. We'll say x1 at the ith iteration, x2 at the ith iteration, and x3 at the ith iteration. Iteration number 0, which we say is initial guess. Most often we pick something that is easy and trivial. Like for example, you can just pick initial guesses to be 0, 0, and 0. So if you use the initial guesses, say x2 equals 0 and x3 equal to 0, what would x1 be? It would simply be b1 divided by a11, right? Now, keep that value of x1. When you move to the next equation, x1 already has a value, this value that you just calculated. x3's value is 0. Using those two, you compute x2. And then when you go to the third equation, both x1 and x2 have updated values. Use it to compute x3. And then you loop this process. You keep doing this until when? When do you stop? When you run out of paper?
Once you're within your margin of error.
What is within the margin of error? Don't guess, say something. Yes.
So I get back into the original equation and hope that it's solved out properly.
More than that, if you say have at the end of an iteration 3 values for x1, x2, x3, if subsequent iterations go on but the values don't seem to change anymore, Isn't that reason enough to stop? That you're doing iterations, but nothing is changing, then why do the iterations? Then you stop, okay? So now let's put all these qualitative things as measurable statements and implement this. So you take this problem and this formula. Compute what is the value of x1, x2, x3 at the end of the first iteration. So at the end of the first iteration, what do you do? So what is x1? X1 would be, what is b1? 7.85 minus whatever it is, x2 and x3 are 0, so it doesn't matter. And b1, a11 is 3. What is 7.85 divided by 3? .6167. And what is x2? X2 would be, what is b2? What is b2? Negative 19.3 minus what is a21? Remember a21 is this 0.1 multiplied by x1, latest value of x1 available. Latest value available. What is the latest value available? 2.6167 plus what is a23 minus 0.3 minus 0.3 times 0, because x3 is still 0, divided by a22 7. Compute this and tell me please. Correct? 2.79 minus 2.7945. Now you compute x3 and then look up. Compute x3 using this formula, and you will have to plug in the correct values of 31, 32, 33 and then b3, with x1 being this and x2 being this. I'll also try. X3 equals Are we also getting 6.327? Maybe not.
I think your A32 value is different. You put
Point
point one, it's gonna be -0.2.
Ah, okay. So what you should have been saying is your A32 value is wrong.
So your X two should be greater than 0.79.
My X is what?
Your X two should be -2.79.
But there is a negative sign already here, right? So negative multiplied by another negative sign, that's why I put those.
When plugging that in, I got 7.0056.
7.0056. So let's take a pause here. I'll give you time to write. And also make sure you understood how we got these three values before we do more iterations. You have a question? No, not yet. So what I want you to do is make sure you understand how these three values were arrived at. We start with our system of equations. We assign them these symbols A11, A12, etc. We rearrange the equations to get x1, x2, and x3. Key thing is there is no universal one way to write this. You can start with x3 and you can base x3 from any equation. You can do this in any order. There is no correct or there is no one order. Anything will work. So you rearrange the equations to get x1, x2, x3, and you do this iteration in sequence, meaning you have an initial guess which could be 0, 0, 0 or something else, any real number. With these initial guesses, suppose first in your list is x1. At that time, whatever x2 and x3 values are available, you put them on the right side. So if I start with the 0th iteration, I'm trying to compute x1, x2 is 0, x3 is 0. With that, I get 2.6167. So this value is based on x2 equal to 0 and x3 equal to 0. And then I move on to the second in my list, x2. At that time, x1's value is 2.6167. 0 is no longer relevant. So I would take this 0 and this 2.6167 and then this 2.7 minus 2.7945 is arrived at based on 2.6167 for x1 and 0 for x3. With me so far? Yes? No? And then I move third in my list where I have x1 to be based on to be 2.6167, x2 being minus 2.7945, and using that I compute x3, which comes out to be 7.0056, that is based on these three values. At the start of your problem, if you decide that this is going to be the order in which you will do the calculations, stick to it. You can decide this in any way. There is no one correct way. That's what I'm emphasizing. Then iteration 1 is done. At the end of it, we have these three values. When you move on to iteration 2 or next iteration, actually before you move on to iteration 2, let's do an important calculation here. I'm going to call it delta x1, delta x2, delta x3. where delta stands for difference between current and previous iteration. What is delta x1? 2.6167 minus 0. So 2.6167 minus 0 to minus 2.7945, 7.0045 or 56, sorry. When we talked about how to stop iterating or when to stop iterating, what we refer to as when this delta is approaching 0, then there is no more need to iterate. That's when you stop. But how to define when it is close enough to 0? That is dependent on the chosen tolerance. Maybe you would want it to go to 4 decimal points or 6 decimal points or whatever. All right, second iteration. Can you please fill this out and provide me these values? In the good olden days, teachers would point to a specific student and ask, can you tell me the answer for this? But now that's putting you on the spot, and I don't want to be called I'm making you this and that. No, I have to just wait for somebody to tell me something. For those that can see how this method already works, you can also try iterating this in Excel. If you can, I mean, doing it on paper in Excel will almost take the same time. In fact, Excel will be faster. So you can also try that, okay? So while I wait for these 3 numbers, I'm going to build an Excel sheet for this. Do we have values for the second iteration? Yes, sir.
The first one I got 0.9906,
9906, that's what I'm also getting.
negative 2.4996.
Yep,
And
negative 2.4996.
96 and 7.0002.
7.0002. Or I would call it 3 because I'm getting 2.9.
Yeah.
Others, were you able to get this? Yes, no, if the answer is no, that's okay. We need to then go a little bit more detailed. That's all. So let's take a pause from the writing. I'm going to show you my Excel sheet and we can see how this can be done automatically. Okay, kind of do it do it by programming. Okay, so bringing back the screen. All right, so I'm going to delete this. So here is our coefficient matrix. This is first column A11, A12, 13, B1, A21, 22, 23, B2, 31, 32, 33, B3. Okay, if you want, I'll just at the top here, I'll index it as A11. This is A11, 12, 13, B1. This is A21, A31, A32, A31, A32, A33, B3. So that's our coefficient matrix. Here is my iteration number and my initial guess is 0, 0, 0. Okay, that doesn't have to be the guess all the time, but it's a good guess for this problem. First iteration, if you go into this box here, I'm trying to say, listen, I'll give you time, okay, and this file will be posted. So let's discuss. F19, which is B1 minus D19, which is A12 times J20, which is X2. So I'm just trying to implement this formula right here. Okay, plus E19, A13, K20, which is X3, divided by C19, which is A11. So I put all that here. The dollar sign, the double dollar sign, is to freeze that cell value so that when you drag it to the next row, there is still F19, but instead of J20, you will have J21 or J22 and so on. It will keep updating. Okay. This routine makes sense to you, right? So now I go to X2, I do the same. So now let's take a pause from this. You try it, those who have laptops until this point, please try and see if you can do correctly for the formula J21. If you can do that, then you're done, basically. Yes.
So does it not like for your initial guesses, it doesn't matter like whatever you use it to be the
Yeah.
forever, that eventually it'll get the right answer.
It's just a matter of degree, meaning it might take a few more iterations. It's like you have an address and you start from very off target. It will take you more time, but you will get there. So I want you to try the formula for J21. If you are able to get the formula right, you will get minus 2.79452, which means you have implemented it correctly. So try this.
You expand downwards, so we can check.
Which one?
You expand the function downwards, but we can check, see if we do.
You mean the J2, J21?
Any of them, so I want to see if I do.
Yeah, right here. I don't know what you might mean by expand.
I think you must be
Could you add?
Oh, you mean the second iteration? Yes. Oops, sorry. So you can check more number of values. Don't worry about iteration 2, 3, 4, 5. You can get I21 and J21. That means your program is working. Next lecture, we'll write this program in MATLAB. Okay, I'm giving you advance notice. You're trying this. I want you to get to I21 and I20 and J21. That's it. Then look up and check your values before proceeding. Those who are just doing it on pencil and paper, you can at least finish the problem and check against these values. Are you able to get these values? Yes. We'll talk about this delta x1 and what that represents also. Just to get a head count, how many of y'all are planning to come to the session at 1 o'clock? About 10. Okay, thank you. Okay, I'm going to give you time until like 12:34. And then I have to continue. This file will be posted, by the way, so don't worry, you are not able to finish. Yes,
Can you go over for a second how to do the dollar sign so it doesn't change? That makes
yeah,
it
sure.
constant.
So if I take my particular value, you can type in whatever formula you want. I'm going to redo this, okay? So let's say I want to do third row, that is x3 f21 equal to f21 minus open bracket c21 times the latest value of x1 plus d21 times the latest value of x2, and then I have to close the bracket one more time divided by a13. Okay, this is the formula you want to punch in. Now you want to freeze the values of f, c, d, and e. So you go to f21, that is, you just put your cursor on this and press F4 just once, you get the double dollar sign. If you press it more times, you will get different variants, but what we need is the F21 double dollar sign. Then you do the same for C21, D21, E21, and then we are done. All right, good. So again, take a pause from writing, doing, look up. So we have a data of first iteration 2.61 something, 2.79 something, 7.005. The delta value is defined as the current minus previous entry. 2.6167 minus 0, which is what the delta value is, the previous value, and 7.005. Now, in this type of problems, I generally don't encourage the use of relative error because sometimes 0 could be a solution to your problem. I really request you to. Sometimes 0 could be a solution which will then lead to a relative error of infinity. So it is best you look at the absolute error and you can keep looking at the magnitude of the absolute error. So as successive iterations go, that difference reduces to 0.37009 and then minus 3.2 times 10 power 5. So you can set your condition something like the stopping criterion could be something like when the absolute value of delta goes below, say, 1e minus 6. You can keep that as your stopping criterion. Now that raises the question, when I say absolute value of delta, which delta am I talking about? X1, X2, or X3? What's the logical thing to say here? Sorry?
You could consider all three.
Consider all three and then?
I mean, you just write that statement. If all three of them are good, then you can write a statement saying proof. You could do it that way.
You can write when the absolute value of the largest of them is less than 1e power minus 6. Then you have three values, right? Just look at the smallest all the time. And if that is less than 10 power minus 6, you stop it. You stop right here. I'm sorry. Not the smallest, the largest. You should look at the largest of the three, and when that is smaller than 10 power minus 6, you can stop iterating. That is, I'll write it in words here. Consider delta max equal to the max value of delta 1, delta 2 and delta 3. If delta max is less than tolerance, or if the absolute value of delta max is less than tolerance, then stop. You can see this, right? It's not too small. Okay. If the absolute value of the largest of these deltas is less than the tolerance, then you can stop. Now, if you look at these values here, you started at 0. You can substitute these three values here, 3, minus 2.5 and 7. You can substitute it back into the equation and you will find that they do satisfy the equation. So they are actually the roots of the problem. Now, it took you, can we say, okay, based on this criterion, when should we stop? Is it iteration 4 or iteration 5? 4. So 4 has values 10 power minus 5, 10 power minus 7. You'll need to go to the fifth because you want the largest of these. The largest is 3.2 times 10 power minus 5. That isn't still yet smaller than 10 power minus 6. You have to go one more iteration where you can say that. So you can write this is the absolute value, or this is the max value of absolute value of delta x1 minus the absolute value of delta x2 and the absolute value of delta x3. Okay. Now I'm going to write a statement. If this is less than my tolerance, 1e minus 6, then what? Then we'll print continue. If not, we'll print, or I'm sorry, if it is true, we'll print stop. If not, we'll print continue. Just putting it like a if statement, it means my error criterion has not yet been met. So my program is saying continue, continue, continue until we reach here, where these three values, clearly their absolute value is 3.54 times 10 power minus 7, which is less than 10 power minus 6. So my if statement says you can stop. Yeah. You had a question about what happens if we give some other initial guess. So let's say we make it minus 100. So if we give that minus 100, minus 100, minus 100 as the initial guess, in 5 iterations, we are not there yet. Maybe we'll add one more and see what happens. In the 6th iteration, we are there. So it took us one more iteration, but that was a very, very off base guess. Like from 0, 0, 0, you went to minus 100 in each direction, but it still didn't matter. Just one more extra iteration. These methods usually are, if your system of equations has a unique solution, this method will most often get you that solution. But if your system of equations has no solution or has infinite number of solutions, then this method will not converge. Okay. So at the start of the next lecture, we'll see how to ensure that a given system has a unique solution. And if so, then you can apply this method. Okay. Questions? All right. So with that, I'll stop for today.